Okay, so I have the pleasure to have here for the colloquium Cara Battersby. Is the more common pronunciation Battersby or Battersby? Battersby, right?
Battersby, yes.
Yeah, okay. Yeah. So I met Cara when I was a postdoc at ISRO and she was a visiting student, and now Cara is a professor at the University of Connecticut in the astronomy department there. She's leading the Milky Way Laboratory Research Group. She got a PhD in 2013 at the University of Colorado, working with John Bally, and then held a couple of postdoctoral positions at the Harvard Smithsonian CFA, where she was also working with a lot of people that we know, Jiyo Zhang, Eriquito, no? She joined the faculty of UConn in 2017, and in the last years, she's the PI or co-PI of several major observational projects on mostly on the central molecular sun, like CMC Zoom with the SMA, ACES with ALMA, 3D CMC, which I guess she will speak a lot of that project. And she's also a co-PI of ALMA-GAL with ALMA. She's been more in the past. She was in the 2017 conference, what we call Enrique's conference, no, in 2017. But today she's given the colloquium remotely. So let's welcome Cara. So please go ahead.
Hi, everyone. Thanks so much for having me here today. I'm really sorry for not being there in person. I feel like virtual is a long, long way away from the ideal situation. But as I'll show in a couple slides, I have 2 young kids at home. So work travel is really, really limited for me right now. I actually loved my visit to Morelia for Enrique's conference, and would definitely come again in the future when my kids are not quite so little. So, and as I told Roberto, like one of the things I really like about doing colloquium visits is getting to hear and like collaborate and like start new projects with people that I meet. And so if anyone is interested in anything that I talk about and like wants to talk more, please reach out. I'd love to like set up a meeting and chat and hear what you're working on as well. So, okay, so today the focus is going to be on our galaxy's dynamic center. And this is like in the middle. Can you guys see my mouse, my cursor, by the way?
Yes.
Yeah, okay, great. So in the middle is like an hydrodynamic simulation that I'll talk a little bit about. And on the right are ALMA observations. So we're finally getting to a stage where we actually have these hydrodynamic simulations that we can compare side by side with these ALMA observations. And then of course, you know, we're doing this in our own galaxy, but these processes are relevant for other galaxies as well. Quick note, organizationally, I see that there's like 6 people in the waiting room on Zoom. Is it someone managing that, or should I do something with that?
If you can admit them, then let them through, but I'm working on it here as well.
It looks like I can admit them. Should I just admit all?
Yeah.
Okay.
Thank you.
You're welcome. I get it's like popped up on my screen, so made it easy. Okay, great. So before we get to the Galactic Center, though, I wanted to show you sort of the roadmap for the talk. So we're going to start at Earth and its humans, and then we're going to talk about the Prima Space Telescope, the solar neighborhood, right in our little home neighborhood, and then the galactic disk. Then finally, the Galactic Center. Okay, so starting with Earth and its humans. I'm not sure how many of you have ever even heard of UConn Astrophysics. It's a new program. It was just started in 2017 with the hire of 3 astronomers, of which I am one of them. We're within the physics department, but now we've grown and we have 5 astrophysics faculty. We have more than 20 graduate students, about 40 current astrophysics minors in our program as well. And you can tell we're legit because Dame Jocelyn Bell Burnell visited us, which is a highlight for me. Come visit us if we're right in between Boston and New York. So if you find yourself on the East Coast sometime, please send me a message, or anyone at UConn. We love having visitors come to speak and collaborate. And it's a really nice campus and facility and a really nice group. And if there's anyone in the room who's applying for grad schools or postdocs, it's a really fun place to live for a while. It's a really fun, inclusive community. So just a little shout out. For other humans, these are the people who do the research that I'm going to talk about today, the Milky Way Lab Research Group. Since I'm in a physics department, when I was applying for jobs in physics departments, people like kind of didn't get it. They were like, well, astronomy is not really physics. And you're like, well, it is, because we use all these physics concepts to do what we do. But because we don't have a traditional laboratory where we can like twist the knobs and then see what happens, the way that we do physics is that luckily the universe is a big place. And so we try to find some place in the universe where the experiment that you want to run is already happening and you observe it. And I think that sort of helped to connect with the physicists in the class in like the room to sort of connect that they, that this was really like astrophysics. Okay, so I'll try to highlight specific people when I present their papers as lead authors, but all the people who are pictured here like contributed something to the analysis, to plots, and to all of that. So they're really the awesome people. Okay, looks like we have someone else in the waiting room as well, but I can see if I can admit them. Sorry, okay. Resharing, sorry about that. Lost my mouse as well. Here we go. Okay. You guys see my screen again? Good?
Yeah.
Okay, great. I wanted to apologize again for not being there in person. This is the reason why. These two little kids, Max and Jenna, 3 and 5 years old, and they are the light of my life. They make me really happy, and I just like to share that because, you know, when you see me up here as like a person who's going to present all this hopefully exciting research, I want you all to remember as well that, you know, research is done by humans and humans have human needs. And for me, I really value work-life balance. I think that's really important. And when I take the time to spend time with my kids, then I find that I come back to work and I'm more productive and efficient during the hours that I have. I have better ideas and I'm more engaged. And so I like to just say that out loud so that people can hear it and know that if they want to make the choice for work-life balance, that there is support for that. Okay, so the next step on our roadmap is the PRIMA Space Telescope. I can see a couple people in the audience. Do people mind raising their hands? Have you guys ever heard of the PRIMA Space Telescope? I see one hand. Okay, a couple hands. So I will give like an overview. So this is something that comes out of the US's Astro 2020 decadal survey. So this was a big thing that was happening, you know, in preparation for 2020. Feels like forever ago now, right, with COVID. But every decade, the US astronomers come together and come up with like, what are our big priorities for the next decade and how do we want to spend the money? And this has been really important for advocating for different missions in the US, and the fact that people all come together instead of competing and all lobby in Congress has been mostly successful for astronomy in the past. That's why we have some of these great missions like James Webb. Currently, it's obviously a little bit different. The government is shut down, and you know, so PRIMA is this far-infrared probe mission concept, and it's designed to be responsive to a new NASA call for missions. This is like a new class of missions that hasn't been around before. It's in the middle. So there's like the big flagship missions like the James Webb Space Telescope, which are about $10 billion. And then there's a smaller explorers. The probe class is about $1 billion size scale. So right in the middle. PRIMA was selected for a phase A study by NASA last year. And so we are moving forward with doing our proposal, doing the very best that we can for hopeful selection, in which case we would move forward towards the next phase of like actually building the telescope. So our official stance is that NASA gave us this money to write this proposal, and we're going to go forth and do it and make it so good that people in the government can't say no, that they have to accept it. So that's the official stance anyways. Okay. So this is a couple of people who are working on PRIMA, the PRIMA COIs, and we have a lot of international partners. We've actually added a couple of new people. I need to update this slide. That was just in the last week. The overview for PRIMA is it's a cold space telescope that's going to operate in the far infrared. And it's about 1.8 meters in size. So it's relatively small, but what makes it really special is that it's going to be really, really cold. So the sensitivity that it's able to reach is totally unprecedented. And we have great coverage of the far infrared in relatively high resolution spectroscopy, mid and low resolution spectroscopy, continuum, and polarization as well. And launch would be 2032 if things are successful. One of the reasons to talk about PRIMA is not just to be like, look at this fancy telescope that may or may not happen, but if it is selected, 75% of observing time will be devoted to guest investigators, to guest observers, and also all of the PI science programs would become, the data would become available right away. And so this is really supposed to be a community telescope for the entire community. And so if it's successful, this is something you can use and be excited about. And you should be excited because it can do so many things. So the thing that really makes me most excited about PRIMA is this detector technology that's been decades in the making at NASA. These kids, kinetic inductance detectors that have just seen huge improvements that allow us to now map out the far infrared at about 100,000 times faster than we could map it out before. And so instead of looking at handfuls of galaxies, hundreds of galaxies, you're looking at hundreds of thousands and millions of galaxies. And I'll talk about the science cases in just a minute. But the sensitivity gain is really huge. And then, as we know, I think many of you know, hopefully, but the majority of light is of dusty objects is emitted in the far infrared wavelengths and can only be observed from space. Actually, more than half of the light from stars that they emit over their entire lifetime gets reprocessed by dust and emitted in the far infrared. So we're not talking about some niche science area. We're really talking about everything that's dusty, and like 50% of all light from stars is reprocessed by dust and re-emitted in the far infrared. It's a hugely important part of the spectrum. It covers like 3 orders of magnitude of, space and wavelength space. So it's a really huge discovery space. So even though this iceberg picture, it's like very good description of like what it would be like, because so much is like hiding under the surface that we just can't see, and we need PRIMA for that. But since we're all physicists, we know that an iceberg like that would just, it wouldn't be stable. That's not a stable equilibrium. So it would go on its side. This is not what icebergs really look like, but it's a nice visual. So the key science that we're focused on is like geoscience is the #1. So this is going to be guest observers, you guys deciding what you think is the most important thing to do with a far infrared space telescope at 75% of the time. And as a reminder, there's currently no operating or planned far infrared mission. So it's kind of prima or bust for the next couple decades at least. One of the key PI science programs is looking at planet formation, so looking at the cool water in protoplanetary disks, and we can measure out the reservoir of planet-forming mass and how the snow line moves, how planets get their water, how they build their atmospheres. Because PRIMA has such great coverage over the far infrared spectra, we can also look at simultaneously how black holes grow, as well as star formation rates in galaxies for hundreds of thousands and millions of galaxies from cosmic noon to today. And we can also look at the rise of dust and metal. So how did dust and metals form in the universe? At what time period? How did that process work? And then the tagline, hope you like it, PRIMA, see what we have been missing. Very fun. We have a really good website. There's a QR code here if anyone wants to grab that for the website. There's also a mailing list where you can keep up to date with everything that we're doing. We have a geoscience book, volume 1, which is a collection of 76 cases that the community put together of how they would want to use PRIMA, and it really covers a broad spectrum of science areas. We are finalizing the editing process for our GeoBook Volume 2, which is 120 cases. That should be coming in fall 2025. All right. So the next step on the solar neighborhood, I wanted to give one example of a geoscience case with PRIMA. And this is focused on the question of how stars get their mass. And even though we have these really nice cartoons that describe the star formation process, there are a ton of really open questions, and there's also some nuances in how this whole process works. So this is like a very idealized cartoon that you see here, and some things that are not reflected here are some of the turbulence and time variability of the star formation process, as in addition to like many other questions that I'm sure all of you know a lot about those questions as well, how stars get their mass. But just, I feel like I could just ask this question, how do stars get their mass? And we still don't really have a satisfactory answer to that. We know that accretion bursts may be important, but we don't really know how important. So some of the lines of evidence that suggest accretion bursts are important are, the first one is called the luminosity problem. This is that if you look at the luminosity of a sample of protostars and you use that to convert to that steady state luminosity, how does that convert to a mass accretion rate? We have some estimates of the stellar lifetimes. You can never get enough mass from the steady state accretion process to get to the stellar IMF that we observe. And so one possible solution is that stars don't just accrete through steady state, but they have these accretion bursts where they accrete more material over short periods of time, and this would solve the luminosity problem. We also know that when we look at protostellar jets, they have knots. They are not smooth, continuous structures that just show a smooth, steady state accretion. You have clumps and bursts of material being ejected from the poles. And we can also see directly accretion bursts. This is an image on the right showing the brightening of a protostar in the HOPS survey with Herschel, and where you have this like very bright accretion burst from the top figure in 2004 to the bottom one in 2008. And this is really best observed in the far infrared. Will Fisher wrote a paper on that in 2023, where he argues that the far infrared is the right place to look for this, kind of the only place to look for this. And so one of my PhD students, Rachel Lee, she wrote a paper that we just got a very positive referee report today, actually. So that should be on the archive within a week, I would guess. And she basically showed with Monte Carlo simulations that if you could use the PRIMA Space Telescope, compare with previous observations from Herschel 20 years ago, and do time monitoring of 2,000 protostars, you could unambiguously answer the question of whether or not a star gets the majority, 50% of its mass, from accretion bursts or steady state. So I think that's a really well-posed question, something you can actually say yes or no. Yes, you get the majority from accretion bursts, or no, you do not. Okay, and so the magic number is 2000, and PRIMA would enable this. So this is just one geocase with PRIMA of, the 120 plus 76 or so that have been proposed. So hopefully you're all a little bit excited about the PRIMA Space Telescope. Now I'm going to say just a couple of words about how the star formation process might vary across the galactic disk. And this is related to the ALMA-GAL program in specific, where we're looking at dense clumps across the galaxy. So about 1,000 dense clumps across the galaxy, 1 millimeter in dust continuum and spectral lines. I think hopefully everyone is pretty familiar with Roberto's work, and their group works on ALMA-IMF, which I think is a very complementary survey. Looks at 2 spectral lines and at a handful of massive protoclusters. And I think that in the next couple years, we can start to compare meaningfully between these surveys and really understand more about the star formation process across the entire galaxy. The ALMA-GAL survey, this is just a picture of from the solar neighborhood, which is right there in the middle, across the disk of the galaxy, that we've selected objects with a range of masses, surface densities, and some are within spiral arms, some are between spiral arms. It's basically just a statistically significant sample of 1,000 dense clumps that show the diversity of across the galactic disk. So 3 to 14 kiloparsecs in radii, and a variety of luminosity to mass ratio. So just like early evolutionary stages to later evolutionary stages, preconfigurations with ALMA, ending up with about 1,000 AU resolution, continuum and spectral lines. Okay, so as I'm sure Roberto knows that, you know, working with these large ALMA programs, it feels like when we found out that that the program was approved, I mean, you just feel elated, like we're gonna solve all the problems. It's gonna, it's gonna be a lot of work, but it'll happen pretty fast. But then the data starts showing up and you're like, oh, it's amazing, it's so great, but it takes a long, long time to process. So these little images here, these are each an individual clump, and we had about 1,000 of them with all of their unique little problems and issues, but finally working through that and coming to some results. Our group at UConn, we are working on the hierarchical structure of these regions. So this is led by Jen Wallace, who's another PhD student in my group. And she has done a dendrogram analysis of all of these different thousands of clumps. And for those of you who don't know, dendrogram is simply a way of taking the fluffy structure in the ISM and categorizing and cataloging it and calculating the properties. It does it in a tree-based structure. So instead of just having individual clumps that are not related to each other, they all are within a hierarchy. So a good example of this is sort of on the bottom here in the middle, where you can see a region that has all this nested structure with these dense star-forming cores on the top. So Jen did this over the entire ALMA-Gal catalog and found that when she categorized things based on, are they very simple and isolated, like the top picture there, we only have 3 little cores that are pretty isolated, versus the bottom picture where you have this whole big nested hierarchy of structures. But you can look at the luminosity to mass ratio, for example, on the x-axis. So the x-axis there shows you very early evolutionary stages on the left to higher evolutionary stages on the right. And there's a clear transition between the things that are richest in substructure to most empty in substructure. A lot of that is probably correlation. It's hard to show causation with anything in astronomy, but she does see some really interesting clear trends. And one other thing in her paper, so her paper is on arXiv now, so you can check it out, but she also makes an argument that her data supports the competitive accretion scenario of clump formation. And it's a little bit more nuanced. So I didn't want to describe it right here in the talk, but her paper includes it. I think it's really interesting and compelling. So if you're interested, I suggest you check it out. Okay, so I just highlighted the yellow paper here. These are the ones that are currently submitted, published in prep. And I think that combining and comparing with the whole ALMA IMF sample is something that I hope will happen in the next couple of years. Okay, so now we're going to move into the galaxy's center. And to start off with, I wanted to talk about how the galactic disk is, here are some properties of the galactic disk. And when you look at it on a specific star formation rate versus stellar mass plot on the left, which is from the FANGS team, the Milky Way is just a pretty normal blue star forming galaxy on the star forming main sequence of galaxies. And it's just pretty standard. And I liked these nice little ladies from Downton Abbey drinking tea. That's like the galactic disk, where there's order and things are well behaved, and you can sit down and drink your tea. And then for comparison, the galactic center is much more like the Grand Theft Auto video game on Wild West shootout mode, where the rules don't seem to apply and there's a lot more chaos and destruction happening. One thing that's cool about that, though, is that the galactic center is, of course, within our own Milky Way, but the properties of the galactic center, shown in the bottom left in the orange, are much more closely aligned to the properties of some high redshift galaxies that we've seen, as you see on the top right there, with much higher surface densities and much higher turbulence, a couple other properties I'll talk about as well. But this means that this central part of our galaxy, the central magnetic zone, or CMZ, allows us to study extreme star formation at high resolution in our own cosmic backyard. All right, so the CMZ is approximately the inner 300 parsecs of the galaxy. This is the side view of it, so looking towards the galactic center and along the galactic plane, you just see sort of this bright region in the middle. That's the CMZ. This is a far infrared image from Herschel. And kind of the first point that I want to make is that our galactic center is really clearly distinct from the disk of the galaxy. So on the right image, this is not a top-down view of our galaxy. I would love to have a top-down view of our galaxy. That would be so amazing. We don't have that. But what we do have is other nearby galaxies where we can see that in this JWST image of NGC 1566, this is a barred spiral galaxy where that central region, and my cursor had been working and then went away. So I apologize about that. But so on the right, there's like that central part within the barred dust lanes there. That is the CMZ and of that galaxy. And it is physically, kinematically separate from the rest of the galaxy. It is just a different part of the galaxy. On the left is sort of another side view of our own galaxy, where you can see that the galactic center stands out in terms of just the mass density. And so there's like that big clump in the middle that's just higher than everything else in the whole inner 40 degrees of the galaxy, so the inner half of the galaxy, and that's our CMZ. So it's really just a distinct part of the galaxy. And another way to think about that or to look at that is that the properties, it's not just physically and kinematically distinct, but its properties are also very distinct. So the gas density, for example, is about 10 to 100 times higher than the disk of the galaxy. You will also have like a much higher chemical complexity. Magnetic field strengths are not microgauss, they're milligauss level, so about 1,000 times stronger than typical ISM conditions, as well as higher interstellar radiation field and cosmic ray ionization rates. The dense gas is hot. So I feel like hot is a dangerous word to use with astronomers because like a lot of people would say 65 Kelvin is definitely not hot, but for like cold, like for like molecular gas that is like very, very dense, 65 Kelvin is quite warm compared to the ISM in the disk of the galaxy. And it's also really turbulent, so about a factor of 10 higher turbulence than the rest of the galaxy. So it's very distinct from the rest of the galactic disk. And globally, we've known for about a decade now that the CMZ is underproducing stars. So in these global comparisons of star formation rate on the y-axis versus dense gas on the x-axis, we think that if we look at the amount of gas that you have and how many stars are forming, there should be a correlation there. People do this all across the universe, which is why you see points on this plot from Milky Way clouds to disk galaxies and high redshift galaxies. And this one in particular is not just looking at total amount of gas, but dense gas in particular. And because stars form from gravitational force overcoming the internal energy of the gas, it's most likely to form in dense gas because it'll have more gravitational energy in that dense gas. And so this correlation between star formation rate and dense gas is really good over many orders of magnitude. And our Milky Way CMZ falls below that by about an order of magnitude. So considering how much dense gas it has, it is underproducing stars by a factor of 10. And because we already talked about how this is maybe like a good local example of what star formation across the cosmos would look like, it's notoriously difficult to measure star formation rates of galaxies at cosmic noon, for example. You have to rely on local calibrations. Understanding whether or not this is a real phenomena is really important and could affect our understanding of star formation over the greater cosmos. So I spent a lot of the last 5 to 10 years looking into this, and I'd say we're still studying it, but some of the key things that we found is that if you look at the overall CMZ, it still falls about an order of magnitude below this. But if you start looking at the individual sort of molecular clouds that are forming stars, you actually fall along the star formation dense gas mass relationship. So our basic conclusion is that in the CMZ, the gas seems to form stars as normal, but there's just a ton of gas that's just not engaged in the star formation process at all. We also studied this with the CM Zoom program that Roberto mentioned. So this is one of the first high resolution interferometric surveys at millimeter wavelengths of the galactic center. You can see a really nice image here, where in red, this is our CM zoom data looking deep within these dark clouds to uncover like the star forming cores. And I'm gonna breeze through the results. We have a bunch of papers, but the basic result is that if you look at the properties of the cores to the left plot, so the mass versus radius, that in the CMZ, the properties of the cores seem to be similar to the properties of cores in the galactic disk, the gray points in that left plot. In the middle panel, you can see some examples of protostellar outflows in the CMZ, which as far as we can tell, are similar to protostellar outflows that you see in the rest of the galactic disk. And now in the right, you can see on the y-axis is something called the compact dense gas fraction, basically just how much of the material of the dense gas is like compacted into cores that can form stars, versus the column density on the x-axis. So the red is everything that's not in the CMZ, and the blue is everything that is in the CMZ. So you can just see that the CMZ just has a much lower amount of its dense gases locked into these compact dense things. So again, most of the dense gas is just not engaged in the star formation process. So to investigate this further, we're doing the ACES project, which stands for the ALMA CMZ Exploration Survey. Gotta love an acronym within an acronym. It's a large open collaboration. If you're interested in joining, just reach out to myself or Steve Longmore. And we're doing a continuous map of the entire CMZ. Here's like a preview of our HNCO data, and HNCO is a spectral line that we think generally traces the dense gas. It's pretty extraordinary. It's a beautiful data set. Here's a cube. So you have like the velocity that you get from the spectral line of HNCO is now projected into the third axis. So you have like an actual data cube. There's so much to explore with these data. We have our first papers coming out in a couple of months, and there's still so much to do and so much interesting stuff to do. So if you're excited at all about this or interested, we're always welcome to new team members. Feel free to reach out and help us explore this new data set. One of the first papers you should see soon is a result that the CMZ is really filamentary. And so this is the same HNCO map, a peak intensity map in the middle. And on the top, you can see 3 zoom-ins towards what we're calling these large filaments. These are things that are contiguous in position velocity space over about 10 parsecs to 20 parsecs in some cases. And these seem to be basically following the orbital streams of the galactic center region. And we also see anytime you zoom in, so we have these 3 zoom-ins on the bottom. This is just looking at almost random 3 regions in the central region here of the HNCO map, where we see just filaments everywhere in the map. And here's, you can see like a more of a zoom in on 2 of those, the SASB2 extended region and the dust ridge region, and just filaments everywhere. So the paper has a presentation of these and basic physical properties, but we still don't know what they are. So if you have ideas that you want to test, like quantitative ideas, I think that would be wonderful to have that conversation. But again, there's a lot to explore here. But it's highly filamentary. So from these like parsec scales all the way to like tens of parsec scales, you're seeing these really highly filamentary structures. This was the spectral line data. We also have dust continuum. So Jen Wallace, who was the one leading our ALMA project, she's also leading a paper with the ACES data, looking at the dust continuum and trying to identify the dense cores. It's ended up being so much harder than we thought it was going to be, because there's contamination from free emission in the galactic center too. So it's actually a pretty complicated process, but she's done an amazing job. And here's a couple of zoom-ins that just show some of the diversity of what you see in this dust continuum and why it's so hard to catalog, count, and get the properties of all the cores. So what Jen has done as part of her PhD thesis is to identify and classify the compact sources in the CMZ to determine their physical properties and to estimate their star formation potential. Then she's comparing that with her ALMA-GAL results of the galactic disk and trying to understand how environment impacts star formation. And here's a preview from her paper of some of the compact structures that she has found. if anyone wants to talk about that further. Okay, I also mentioned that we're working on magneto-hydrodynamic simulations. This is being led by Danny Lippman, who's a UConn PhD student. Both her and Jen Wallace are actually graduating this year. They're both phenomenal. If you are hiring, I will be writing a very strong recommendation letter for both of them. They're awesome. So these are magneto-hydrodynamic simulations of the galactic center, and this is a building on the work from Matthias Romani and Robin Tress, who had papers in 2020 of CMZ simulations. This is now just much higher resolution, so we can actually compare with the ACES data, look at the star formation as it's occurring. She includes both star and sync particles. And in this simulation, we're getting into the high resolution part now, but the first thing that happens is that we are forming the bar, and you can see that there's gas on the left panel. We actually have like a galactic disk, and material is flowing in from that galactic disk into the central region. And then we have like an adaptive resolution. So we really just see like the highest resolution in the very central part. So one of our main focuses for doing these simulations was to be able to do like side-by-side comparisons of the star formation and to understand the star formation properties. And that is still something where Danny is finishing for her PhD thesis. So I'm not going to spoil any of her results here, but one of the things that I wanted to bring up with these simulations is that this region is highly dynamic. And this is very different from galactic disk star formation in ways that I hadn't fully appreciated until we were doing this project. So not only is it just different physical properties, but the dynamics are incredibly important here. For one, the dynamical time of like how quickly the gas is orbiting around the center is approximately the same time scale as the star formation time scale. So clouds are forming and being destroyed on the same time scale that the stars themselves are forming. You constantly have an influx of material and turbulence that continues to shake things up. And so it's like the opposite of a steady state process. There's no steady state. There's no steady cloud that then collapses and has the same star formation process. It's really a different process. And so these galaxy centers are highly dynamic. And I think we knew this already from looking at nearby galaxies. You can see a wide range of variety of what their central regions look like. And also in more distant galaxies, we have like the Hercules A AGN on the bottom left is an AGN. So some galaxy centers their supermassive black holes are actively feeding and have feedback. The NGC 253 starburst on the bottom right is a galaxy center that is undergoing a huge burst of star formation. And so I'm really interested now in trying to figure out what controls the cycles of the gas inflow, the star formation, and the outflows. And the reason for that is I started from the star formation perspective, but you really can't understand the star formation without understanding all of these features together because it's not separate, it's part of the same process. And one of the hypotheses for why the CMZ star formation rate is low compared to the amount of dense gas that it has is that the star formation rate may be episodic. So if you have a much more highly turbulent gas that is also hotter, that means that your gene's mass increases. It becomes more difficult for gravity to overcome those internal forces and collapse and form a star. So if you have a constant influx of material, you keep throwing material in, it's not quite dense enough to overcome that higher threshold for collapse. More material, more material, more material. Eventually you get high enough where you can overcome the internal energy of the gas, have a huge collapse, maybe have a big burst of star formation, which then blows out a bunch of the material. And then the process starts over again with gas continuing to flow inwards. And so you really can't understand the star formation without thinking about the larger dynamics as well. So I'll talk a little bit about the dynamics today, but it's really started in terms of trying to figure out the star formation. We also know from simulations that when the black hole has an opportunity to feed on material, it's also going to depend on the star formation, so how that gas gets in. So this is a cartoon made by Betsy Mills of this dynamic galactic center, and really any material that wants to get into that supermassive black hole has to pass through the centromolecular zone. It has to pass that gate and somehow get into it. So we have these four features. So we have gas inflow from the disk to the CMZ itself, star formation within the CMZ, which can drive material inwards because if a star forms and has feedback, then some of that material will get driven towards a black hole. And you have outflow from the galactic center and of course inflow to the supermassive black hole. So I already talked quite a bit about star formation. Our current estimates of the rate of star formation is 0.07 solar masses per year. There's still a lot of open questions, but that's all I'm going to say about the star formation for now. I'm going to talk a little bit about the gas inflow to the CMZ, how the gas gets from the disk of the galaxy into the CMZ. And this is really funneled by the bar. So we live in a barred spiral galaxy, and that bar, as it rotates through the galaxy, basically causes like friction. And so some of the gas in the disk loses angular momentum and gets driven along the bar. And it falls along these X1 orbits. And then the CMZ is this sort of central elliptical type orbit perpendicular to that, and something called an X2 orbit. So it's all mediated by these bar dust lanes. The bar is mostly a stellar feature, but the gas moves along the bar. It's still driven by that gas, by that potential. Okay, so this is our side view of our CMZ in the center there. And this is looking at in the NGC 1566 galaxy again. Hopefully you can see those two dust lanes that are feeding from the disk of the galaxy into the center itself. So these X1 and X2 orbits, these bars feeding into the galactic center, are common in all barred spiral galaxies. And you can read more about that in the Schinnerer and Leroy review paper. So we can measure this gas inflow by using both simulations and data. So H. Perry Hatchfield and Sermani and Barnes combined the data itself with basically a model of how you connect the kinematics to an actual inflow rate to calculate a gas inflow to the CMZ rate of 0.8 solar masses per year with a very large error bar. We also know that there's gas outflow from the center of the galaxy. We have these beautiful examples of Fermi bubbles. I just pulled up a recent reference from Gabriele Ponti in 2021. I think the rates of this are still pretty uncertain, but something in the order of 0.6 to 0.8 solar masses per year. So this is like these giant bubbles above and below the galactic center that are probably related to previous AGN feedback, could also be related to star formation feedback if you have a huge starburst that happens episodically in the centers of galaxies. And we also know that our own galactic center has had activity in the past. And this evidence, in part, not is just from these Fermi bubbles, but also from active time domain X-ray observations. So over the past 20 years, X-ray observatories have been studying the galactic center and seen variable emission from cold molecular clouds. And what's happening in these clouds is that the, actually, let me just show you the variable emission first. This is an image from Micah Clavel. You can see 3 different time spans in red, 1999 to 2003, green, 2004 to 2007, and 2008 to 2011 in blue. You're actually seeing individual molecular clouds being fluoresced by X-rays. So the idea, here's a little cartoon, is that supermassive black hole at the center of the galaxy, when it has some kind of accretion event, it will emit X-rays because the accretion disk gets really hot and emits X-rays. These X-rays travel in all directions, and only the ones that came towards Earth were not observed because we didn't have X-ray telescopes at the time, but the ones that went sideways or like slightly forwards and slightly backwards in the galactic center then interacted with the molecular clouds, caused those molecular clouds to fluoresce, and then re-emit those X-rays back towards us. And then we could see that as actually variable X-ray emission in the molecular clouds. Here's an example of that towards the Styx molecular cloud, where you can see from 2010 to 2017, the variable X-ray emission, which I've highlighted with these contours. And what we're actually doing with this X-ray emission is we're actually mapping out the cloud. So it's like an X-ray scan of the cloud where every year gives you a different slice of that information. And yeah, so it's like X-ray tomography. So now those same exact contours in like the purple contours on top, and in the background now is molecular line data from the CM Zoom survey. And you can see there's actually really good correspondence at high resolution between the molecular features and the X-ray emission. So we're really tracing out individual clouds. But because we have, the X-ray has like timing data, the distance between the sections of the cloud that you see is just determined by the light speed travel time. And so you actually get like a third dimension in astronomy, which is usually really, really difficult to get. And so we can map in these 3 dimensions what the cloud actually looks like. So this molecular cloud tomography is a really fun way to understand like the 3D structure and turbulent properties of these gas clouds using this unique method. And then one really cool thing about this as well is that the distance between the cloud and Sagittarius A star, it tells you when an X-ray flare happened. And we don't know if Sagittarius A star had a lot of X-ray flares in the past or not very many X-ray flares in the past, because we don't know the distance between the Sagittarius A star and those clouds. So we need to know the 3D structure. And if we did, then we could use those flares to tell us, hey, there was one past accretion event on Sagittarius A star, or 2 or 3, or however many there were. And in order to understand that past feeding activity, we need to know the 3D structure. Okay, I would also argue that in order to know the future activity of the supermassive black hole, we also need to have that 3D structure. Okay, here are some estimates. They're pretty vague, but this is the goal eventually, not yet, where I'm wrapping up this talk, but this is sort of the future goal in my group, is to try to figure out all of these rate terms. And so one of the things we've really focused on is looking at the 3D structure of the CMZ. You know, we only really get this side view here, and then on the right here is 3 possible top-down perspectives from the Johnny Henshaw's review paper in 2023. And this really matters because if you want to find gas that's actively flowing in towards Sagittarius A star or understand the past accretion events, you really need to know the 3D structure. So we have a series of papers on this 3D CMZ structure. You can follow along on our GitHub webpage here. We have all of our data and code and our models and even a 3D viewer available on the website. A lot of this work was led by Danny Lippman, who's, again, the same Danny who's doing the numerical simulations, a PhD student, and Dan Walker, who was a postdoc with me for a while. And yeah, so I think in the interest of time, I'm going to skip forward past some of the details of the 3D CMZ stuff, and I'm just going to go straight ahead to, actually, I'm just going to, give me one second. All right. Yeah, so lots of information on the papers, but we basically created a whole catalog, calculated other properties, and then used extinction of spectral lines and dust emission to identify if clouds were on the near side or the far side, and combined all of these in a Bayesian framework. So we have an estimate of the near-far likelihood for every cloud in the CMZ, and then Danny has now created a full new X2 orbital model, which is like our first view of the galactic center from the top down, which we can then use to understand gas that's flowing in towards the center and previous flaring events on Sagittarius A star. We have a fun machine learning project which we're trying to use these simulation snapshots to teach a neural network to be able to take the longitude velocity projection of snapshots and to learn the top-down projection of those same snapshots. The simulations are nice because we have like hundreds of thousands of snapshots, so you can really build up a neural network. And we have a lot of work to do on this, but so far, this is a simulation snapshot that was not part of the training set. And we've been able to demonstrate that you can pretty well do the top-down reconstruction. So compare the image on the right with the image on the left, which is the true top-down image. So it looks pretty good. And just one more example of that. Okay, so in the future, you can expect to hear more about hopefully these like structure equations and like how the gas is flowing. And that will also tell us more about star formation and future inflow. And for now, I will leave up my summary. Thank you so much for your time and attention and for having me as a visitor. Happy to take any questions. Thank you.
Yeah. Okay, so let's take questions from the audience. Raul.
Hi, thank you very much for your talk. I would like to know about the simulation that you presented when there was this galaxy, spiral galaxy, and when you show several zoom, and it could be seen like several bubbles going up, and then what are these bubbles produced by? Could it be supernova explosions or the star formation of massive stars, or why they appear and disappear?
Yeah, that's a great question. So they are, I didn't mean to unshare my screen, sorry about that. They are star formation, like supernova bubbles. And so this is like a part of the, so in the simulations, we start at lower resolution and then move to higher resolution. And then when we do move to higher resolution, we start including individual sync particles for like individual stars forming in the simulation. And so you can sort of see this transition to like when those all turn on, then you have these bubbles form. And so, you know, you don't study that part of the simulation quite yet. You want to wait for it to equilibrate a little bit more, but those are exactly, that's exactly right. That's supernova feedback and just general stellar feedback from the forming stars. Great question.
Thank you very much.
Okay, I have one. Well, So you mentioned like a couple of pieces of the puzzle that I want to see if they fit together. So I mean, we know that the global star formation rate of the CMC is smaller, but then when you look at the individual clouds, they fit very well in the Gauss-Solomon relation and in the Koenig-Schmidt relation.
Yeah.
So then what happens is that there is a lot of dense gas that doesn't participate directly on star formation.
That's right. Yep.
And then later you mentioned that it seems that the overall lifetime of molecular clouds in the CMC is probably shorter than the typical. So how these several things fit together? Is there already like is the global star formation rate lower because molecular clouds live shorter and there is less time for core formation? And is there already like a coherent picture of these different?
There is, yeah, you're asking exactly the right question. So I mean, let's write a paper on it. Like we don't know. And I think that in particular the question of how long lived are the clouds in the center actually hasn't really gotten very much attention in the literature, and something I feel like I should have realized earlier, but I'm only starting to realize is that you know, the clouds themselves are not sticking around, which I think should have a pretty big impact on that star formation process. And so the story in my mind, like several months ago, was really just that this episodic star formation made a lot of sense in the sense that you have, it just takes a higher density since you have a higher internal pressure in order to form stars. And so even though you have like quote unquote dense gas, it's like not dense enough to overcome this higher internal pressure of CMZ clouds. And so when you do have the star formation, it proceeds as normal, but then a lot of that gas is just not past that threshold. And so if you had an episodic star formation, that could make a lot of sense. But then the thing that's been on my mind lately has been exactly what you said, like the idea that these clouds may not be lasting very long and what is the impact of that? I don't think that's something I plan on looking at. And if you want to talk about it more, I'd love to get your thoughts on it because I think it has to be important, but I definitely don't have there's no narrative on that yet.
Okay, thank you. Javier had a question before. It was Ruben, Javier. Yeah, who was first? Ruben. Okay. Yeah.
Hi, Cara, thank you for that. When you show the images from the ACES collaboration, there is a very high transition, I think, from HMC.
Yeah.
Why is so high this transition? Is because the high density or the high temperature?
Yeah, great question. So the HNCO 4 to 3 is a very high energy transition for ISM clouds, and that's the reason that we see it so widespread in the CMZ is because the density and the temperature are both highly elevated compared to the disk of the galaxy. So it would not be a good choice. And actually, I think in the ACES spectral band, we we either have one of the CO lines or we like excluded the CO lines on purpose because a normal tracer like CO 1 to 0 is just going to be optically thick almost everywhere in the CMC. So you actually have to go to rarer molecules and higher transitions to even see optically thin radiation. It's a really good question.
Okay, thank you.
Okay, Javier.
Yep, I didn't understand properly the X-ray emission thing. I mean, you mentioned that it's a way of tracing a former activity in the central zone, then probably in the black hole.
Yeah.
Is that correct? What I understood?
Yeah. So like the X-rays you're saying?
Yeah.
Yeah. I think so. That's what we think. There's point source X-ray activity, which could be any number of things, the point source X-rays, but this is more like widespread, diffuse, and associated with molecular clouds. And that's what we think is this fluorescence. Yeah.
But how long ago? I mean, the Fermi bubbles and that stuff it apparently occurred like 4 million years ago. I don't think this is that old, no?
Yeah, these would be longer, more distant. So talking about like probably hundreds of years in the past.
Mm-hmm. Okay.
Jacopo. Gilberto.
Thank you. So the interpretation is that there is a lot of dense molecular gas that is not currently involved in the star formation event, episode, activity, etc. So if we look at other CMCs in other galaxies, we won't distinguish the individual clouds. We will just see a lot of dense gas, and we will see a low efficiency also. So why don't we see that? Why don't the relationship go down for unresolved CMCs?
Yeah, it's a fabulous question. And I feel like I've been bugging people in the FANGS group for almost a decade to say, are you guys doing this with your FANGS galaxies? Because you really need to do this. And they know, and I think they have actually put in a lot of effort in the last couple of years. I think we're going to see some results from the FANGS group on nearby galaxies of like what the CMZs are doing. So these extragalactic CMZs were largely from like Maria Jimenez had a paper where she combined a bunch of these from an IRAM 30-meter survey. So this is not, I would say a lot of them were not fully resolved. And, you know, you do see some spread in the extragalactic CMZs. I think that it's, the jury is still out. So I think that this whole narrative is still being filled in. Early, you know, the things people have just told me that they do see like some variety, like they see up and down. And so they see some that are below this Gauss-Solomon line and some that are above it, but that's not published yet. And I think that they're still figuring out for themselves what that actually looks like. I also wonder in our own galactic center, you know, we have like a really good estimate of the star formation rate, but we may actually have like too good of an estimate, like some of the more diffuse emission that if you were looking at it from the top down, you might say, oh, that's part of this emission. I'm going to include it in my star formation rate conversion and add it to the star formation rate. It may be that we can actually see better how low it is, whereas other galaxies you would resolve that. But yeah, this is like active area of research, definitely not completed understanding of this. I think you raise a really good question.
Thank you.
Okay, so can we finish with Jacopo?
No, I have the same. I have the same questions.
It was the same question. Okay, so
There's also a question.
Enrique, yeah.
yeah, I guess he can unmute himself.
I can. He can.
Okay. Yeah, go ahead, Enrique.
Gracias, thank you. So hi, Cara, great talk. Really fascinating stuff. So I have like 4 questions. So you guys tell me how many of them I can ask. But the first one is, of course, you mentioned the fact that the velocity dispersion in the clouds in the CMZ is very large. And we always refer to it as turbulence, but as you probably are very well aware, I always question whether this is real turbulence or some form of more organized motions. Could it be thought more as like cloud scale motions, like shear rotation or tidal disruption? Because in fact, Javier has talked about the fact that when an object is in a tidal flow, it may be actually getting tidally disrupted. So, so the other question, in fact, was: is there kinematic information that we could use to distinguish what type of motions do these clouds have to really be more precise than just calling them turbulence?
Yes, I mean, you're exactly right. Totally in line with everything. And it's very much an open question at this point. So I think the ACES data can do a lot to help answer this for us. So, you know, like this nice movie here, if we do then the work to try to like identify, basically to do like a size line with relationship on this kind of thing, I think you can say a little bit more about turbulence, but you know, starting in this field, I felt like people really knew what turbulence meant when they said that. I was like, well, what do they really mean? And for so long, I just thought, well, what am I missing? What am I missing that I don't really get it? And then A, turbulence is complicated, and B, people kind of use it loosely, like the way that I did in this talk. And so it is really gas motions, and most of them are just velocity dispersion. So it's literally the velocity dispersion is higher. From having looked at the data with ACES, I can say that like even on the small scales, the velocity dispersion is high. So some of that still could be shear motions or rotation, or even gravitational infall could be confused. It does cause higher velocity dispersion. So I think a lot more specificity is required on that. I'm not sure you're going to get those answers really soon, but you should work with us and help us with that, because yeah, it does seem to be widespread though. Small scales, medium scales, large scales, you do have higher velocity dispersion. So I think in order to say whether or not that's turbulence, we probably just need to like better define what we mean by turbulence.
Exactly.
Yeah.
And so in fact, now that you're doing the simulations, I was wondering, perhaps you can answer some of those questions, at least in the simulations. So what kind, because I see that the clouds are undergoing a lot of shear, and you're right, they're coming and going really quickly. And so I think it would be fantastic to try to understand what's really going on in the simulations, because that could give us a clue as to what type of motions are happening in the clouds. No, is this something that Danny, for example, is working on?
Yeah, so Danny will not focus on this for her PhD thesis. Actually, if you remember H. Perry Hatchfield, he did a PhD with me a couple of years ago. He's actually coming back to the research group as a research scientist after a stint in industry. And he's always been really interested in turbulence. So I'm hoping that over the next year, he's actually going to write a paper or two looking at the turbulence in the simulation. So he will be looking into that. But again, I'll say, if you're interested, we should talk, because I think that there's a lot more to be done on that.
Okay. Yeah. And perhaps my last question concerning the simulations is, do you see episodic star formation events in the simulations that could explain the speculation that it can be so in the CMC?
Yeah. So I'll give as brief an answer as I can. It's a little bit nuanced. So there have been 2 papers that I'm aware of that are basically cosmological zoom-in simulations, where they take small volumes of cosmological simulations and do like galaxy zoom simulations on those. And both of those 2 papers, one by Matt Orr and one by Paul Torrey, they both saw variable star formation rates in the centers of the galaxies, and they saw like this clear like buildup of material, huge bursts of star formation, clearing out of material. They both saw this cycle on like 10 megayear timescales. There's also a theoretical paper by Mark Krumholtz where he argues that this should happen in these galaxy centers. There's 2 other simulations whose like names and dates I'm blanking on, but they also, one of them saw this episodicity and one of them didn't. In our simulations, we haven't looked at it with these new high resolution zoom simulations with Danny. That's something that she will be looking at in the next couple of months. But in the papers with Matthias Ormani and Robin Tress, before we had the high resolution, we didn't see a change in the specific star formation rate, but But that was because the amount of mass that's in the galactic center does vary significantly, and the star formation rate varies with that mass. And so we saw that variation in the star formation rate, but it was tracked directly by the amount of mass that was there. So we didn't see like a changes in the amount of star formation per dense gas mass in those simulations. But I think that it's something to investigate with the new simulations. So I would say, yeah.
That's interesting because we see something similar in my former postdoc simulations of dwarf spirals. We see different star formation rates, but the same specific star formation rate per for the dense gas. Yeah, so this is interesting. Yeah, great. And I don't know if I have time to make one last question.
I think we need to wrap it up, but I guess we can communicate with Cara by email.
Yeah.
Okay.
Yeah.
I'd be happy to chat more.
Thanks again to Cara. Thanks, Cara, for the great talk.
Yeah.
Thank you guys so much for having me, and please do reach out to follow up. I'd love to chat more with anyone who's interested. So thank you so much for having me. Appreciate it.
Great.
Oh, thank you.
Good to see you. Bye-bye.
Bye.
En las simulaciones de Leo,